theorem, the converse is what comes out of Bloch-Davidson 4, that if these two invariants are zero, then the cycle is rationally equivalent to zero. So in that sense, it's like an extension of the classical Hubble's theorem. In the general case, if you assume that X is defined over the rationals, and use the Q decomposition, so we have a variety defined, smooth variety X defined over Q, we have an algebraic cycle defined over K, and we do the spread construction. Here now you really do need to think about the ambiguities that arise in the spread construction. And the technical word is to use existing theorems about the homology of algebraic variety. In particular, both the Lefschetz theorems have to be used, affinity decomposition has to be used, and the fact that you're working with a spread. The fact that you're working with a spread comes in that if you take the family of algebraic varieties as a spread, then a Hodge class is absolute Hodge. Hodge conjecture implies that it's an absolute Hodge, so it's invariant. Then you move. So taking the Q decomposition and taking out the ambiguities, you organize that by the following picture. This is beginning from the cohomology of X in top degree. This is in degrees 2p and 2p minus 1. And you organize, so to speak, the first half of the Q decomposition by this picture. So this is in degree 2p. This is in degree 2p minus 1. Now, ordinarily, when you want to take the homology of a cycle, the cycle has to be homologous to zero. Here, a little remark is that in the tensor product, if the first pieces here are in the fundamental class are zero, then the first pieces in the Jacobi are defined. So we saw a special case of that. The classical special case is that if this is zero, that's the fundamental class, then this one, which is the Jacobi, is defined. This doesn't really enter. It's there, but you don't see it classically. You can consider it, but you don't need to. The case of zero cycles on the surface, this was the trace, the Mumford invariant, and that being zero was necessary that this be defined. And that's how the picture goes up the line. So the filtration on the Chao-Group as we propose is defined by this picture, the part lying under the brackets. And the successive quotients are defined Hodge-theoretically by this. And the fact is that if you have an algebraic cycle for which all of this stuff is zero, then using the general Hodge conjecture and the Lefschetz theory and so on, you can replace it by a rationally equivalent cycle defined over Q bar, within X is defined over Q, for which the fundamental class on the product and the Jacobi on the product are zero. And then the fourth part of Bloch-Davidson tells you this is rationally equivalent to zero, and then that implies that the original one is. So here the point is that all of what you don't see in this picture is in the ambiguity. So all that you need to consider if you have the fourth part of Bloch-Davidson is the Hodge-theoretic pieces that are in this picture here. So, for example, if you have a class that's at filtration level Q plus 1, and it's defined over a field that has degree less than H or Q, then it's rationally equivalent to zero. That should be Q plus 2, I think. So for Q equals 0, that's the fourth part of Bloch-Davidson, and this is just an extension. Conversely, if you have something that's in filtration level Q in the Chao, then it's the sum of cycles defined over fields of transcendence degree Q. So it's really saying that in the case of the surface of the varieties defined over Q, the filtration and transcendence level of cycles are roughly the same. So as a small application, if you have a zero cycle on a field on a surface defined over Q, and if the second on a regular surface, I left that out, on degree zero, and if the field has no homomorphic Q-forms, that's independent of which model you take to the field, then the cycle is rationally equivalent to zero. So that's the sort of thing that comes out of this construction. So the conclusion then is that for higher coordinations, the field of definition enters into the Hodge theory of the Hodge-theoretic invariance of the cycle. If you have a variety that's not defined over Q but defined over any field, you have to take the spread both of the variety and of the cycles. And the original argument that Mark and I had was not complete. It was completed by the referee in the paper using Margita Saito's mixed Hodge motif papers. Since then, a more elementary argument has been given by Di Cataldo and Migliorini using the decomposition theorem of Davidson, Bernstein, Doreen, and Gomber. So I think in general now this picture that I did with this unit can be done if you use a very tight filtration or the thing coming out of the decomposition theorem. Finally, I'd like to talk a little bit about some of the implications of the Hodge conjecture on the geometry of normal functions. This is an old story, normal function story. So I'll say historically back to Poincaré and then Lefschetz. And I'll give a bit of a history as I go on. The point, though, will be to say Okay, suppose that the Hodge class comes from a cycle. Then what can one say about the geometry of a normal function associated to the Hodge class? So we're going to briefly recall the definition of normal functions, or classical definition, and generalize that to what I'll call extended normal functions. And then if you look at an even-dimensional variety in projective space, and here we're allowing ourselves to reinvent it with higher degree as necessary. That will come out of the argument and blow up blow up as needed in the space of hypersurface sections. This means that you're fibering your even-dimensional variety by odd-dimensional subvarieties. And in this case, the primitive part of the Hodge group will be isomorphic to the extended normal functions. So to each Hodge class, there's one of these objects' extended normal function. So that'll be the first point. The second point is that an extended normal function has a singular set. And the singular set only appears in codimension 2. You don't see it when you have a one-parameter family. And moreover, if a Hodge class comes from a cycle, then if you take a high enough degree embedding in projective space, the singular set is not empty. You can describe the singular set, again, always assuming that the Hodge class comes from a cycle. You can describe it in the following way. That if you look at it most, and this will be sufficient when we're doing it, most nodal hypersurfaces, the singular set, are the nodal hypersurfaces that support an algebraic subvariety of dimension n, so for dimension n-1 here, that has non-zero intersection number with the Hodge class. So the singularities are picking up the hypersurfaces that support cycles with non-zero intersection number with the Hodge class, assuming the Hodge class itself comes from a cycle. And finally, if time permits, I want to talk a little bit about the normal function, pulling back some of the universal objects that are defined, the Poincare line bundle and the Pape line bundle, and relating those to the group law, or the group structure on the space of normal functions. With regards to that last point, the geometric implications of the normal function of a Hodge class coming from a cycle on what the pullback of these universal bundles is not understood. It's a question, but it's certainly not understood. An extended normal function, so this is going to be something defined over smooth variety S. And in the variety, we have a divisor that will have what I'm going to call quasi-local normal crossings. Quasi-local normal crossing is like normal crossing, except you don't have to have the hypersurface system always form part of the coordinate system. You have to have transversality, like here, so it's an extension of local normal crossing. And we'll look at the variation of Hodge structure of weight 2n-1 over the smooth part of the variety. And the most important thing is if you assume that you have a point on the discriminant locus that the monodromies around the branches, they're not singular, but they don't necessarily form part of the coordinate system, but there is a transversality, the monodromies should commute. So that's quasi-local normal crossing. And then there's canonical extensions of the sort of variation of Hodge structure of the open part across the discriminant locus. Done in the geometric case by Menefti and Steenbrink, and using the work of Kahane, Kaplan, Schmidt, Peshuar, and others in this variation of Hodge structure case. The upside is that the Hodge bundle, the Hodge filtration, the Gaussian connection extend to the whole complete parameter space. Over the non-singular part, one has the sheaf of sections of the family of intermediate Jacobians, with a condition on what happens when you locally lift the section of the quotient to the cohomology, what happens if you apply the Gaussian connection. That's the point here. So classically, a normal function was a section of the sheaf of Jacobians, or intermediate Jacobians, over the smooth part, with the property that around the point of the discriminant locus, it should lift in a single-valued way. And I'll denote that sheaf by JE, sort of the extension of the sheaf of sections of intermediate Jacobians across the discriminant locus. Where these arise from geometrically is the following. If the variety has dimension 2, and if you have a primitive algebraic cycle, an algebraic cycle whose fundamental class is a primitive class, that means you intersect the cycle with a hyperplane section or a hypersurface section, and it's homologous to 0. If you take a Lefschetz pencil, this was the classical case, that means that you have finally many singular fibers with one node. Then this class is still 0 on the node. You can think of it moving in a right equivalence. You don't change the fundamental class, and you can move it off the node. The normal function then given by the algebraic cycle is the point in the intermediate Jacobian corresponding to this algebraic cycle that's homologous to 0 on the fiber. So you think of an algebraic surface and an algebraic 1 cycle on it, whose intersection with each fiber is a divisor of degree 0 on the algebraic curve, and take the point in the Jacobian. It's an extension of that. Over the nodal hypersurface section, you have the generalized Jacobian, which is a C-star extension of the intermediate Jacobian of the canonical desingularization. So I left a little gap there, meaning it's not compact. So these normal functions in the classical case of curves on the surface were what were used by Lefschetz. They were introduced by Poincare, exactly the type of curves on the surface, and were used by Lefschetz in his proof of the 1-1 theorem. For n bigger than or equal to 2, the normal functions have been of limited use, I think, because of the failure of Jacobi inversion that I mentioned earlier. So Lefschetz says that if you have a Hodge class and it comes from a normal function, if you use Jacobi inversion with dependence on parameters, that traces out a cycle on the surface, and that was his proof of the 1-1 theorem, the idea behind it. But that doesn't work in higher dimensions because Jacobi inversion fails. So I want to talk now about what extended normal functions are and then do a few speculations. This notion of extended normal function is again something that goes back some time. I think Ron Zanaghi and I worked on this many years ago. But at that time, I think that, at least for me, the foundational understanding of how a Hodge function degenerates over a high-dimensional base wasn't really in place, and one really needs that to make sense out of this. Where is the... So the extended normal functions, an extended normal function is given by a normal function over the open smooth part. And around the discriminant locus, instead of saying it has a single value lifting, what you say is that when you take any generator of the fundamental group of the discriminant, and you analytically continue a lifting around that, and you allow yourself to multiply by an integer to get rid of torsion, that should be in the image of monochromy minus the identity of the cycle. So it's saying that you lift this normal function and you analytically continue it, that should be modulo torsion, the same thing as the monochromy applied to the cycle, but that cycle depends on which element of the local fundamental group you have. So for one-dimensional base, because you have only one generator of the local fundamental group, this turns out to always be satisfied, considered a consequence of the Clebyshev exact sequence. So extended normal functions and normal functions are the same over a one-dimensional base. What the Clebyshev exact sequence says is that the vanishing cycles and the invariant cycles are essentially the same up to torsion, and that's the basic fact that's used here. But over a higher-dimensional base, they may be different, and that leads into an exact C sequence with some function which is supported in codimension 2. By definition, then, the singular set of extended normal function is the support of what it goes into here. So the basic facts are first that a Hodge class is an extended normal function. Consequently, it was known for Lefschetz pencils that a Hodge class gave a normal function, something specific I worked on many years ago. There's a general form of that for any family of varieties with a one-dimensional base and any singularities, but using normal functions was done by Steve Zucker. That's the definitive form, really, for the theorem on normal functions with one-dimensional base. And what one has to do here is to just see that you, in fact, get an extended normal function if you allow high-dimensional base. That's the first fact. The second is that if you have a Hodge class that goes to the cycle, then the singular set of the extended normal function is not empty for high-degree hypersurface sections. Okay, so somehow having that cycle generates singularities of this extended normal function. The way it generates the singularities, roughly speaking, is to have a singular point means that the intersection of the cycle with the fiber is not homologous to 0. And that then creates singularity for the normal function. So I think this suggests, and this is really speculation, studying the geometry of the singular set. What is its codimension? What is its fundamental class? Now, the singular normal function is a Hodge theoretic object. And the fact of a Hodge class, you have a normal function is something formulated purely Hodge theoretically. And at least in principle, the work that has been done and is currently being extended by Kato and Isui on partial compactification of reclassifying spaces for Hodge structures would say that the singular set is the pullback of some boundary component in this partial compactification under an almost Jacobi type map. So if this Kato-Isui theory works out as it does in the classical case, so that it occurs on the surface, then you'll have an estimate on the codimension of the singular set. If it's not empty, then the codimension will be bounded from above by some Hodge theoretic quantity. And I'll say what that is in the classical case in a minute. On the other hand, if a Hodge class comes from a cycle, then the singular set has an algebra-geometric description. And so it has codimension that you can write down in terms of homology and so on. It's an algebra-geometric object. So that will give you some relation between an algebra-geometric object, a number, and a Hodge theoretic number. So let's just take the classical case of curves on the surface. then by semi-stable reductionism, you can always assume the singular fibers are total. And the codimension of the singular locus turns out to be the number of nodes over the correction from the H20 of the surface. The number of nodes is the expected codimension, because when you look at the boundary of moduli curves, you have a k-nodal curve. Those are codimension k of moduli. So there's some correction of a Hodge theoretic curve, of a Hodge theoretic nature. And where that comes from is that one should look not just at an isolated surface, but we should let the surface vary in moduli. So suppose the surface has some moduli space, and the surface is sitting in a big projective space, you let that vary over moduli. That's a strict S, which you'll see small s on the regular S before. In the moduli space, you have the so-called Noether-Lefschetz surface. That's the sub-variety where you have your Hodge class remaining a Hodge class. When you vary an algebraic surface, you have a curve on the surface that usually disappears. When you move the surface, that Hodge class usually also disappears. You look at the sublocus of moduli, where it remains a Hodge class. This is an algebraic subrising by theorem again of Galili, Catania, Kaplan. And in this larger object, where you let the normal function vary also over the Noether-Lefschetz locus,